Welcome to the Bytecode. I'm your Shafu, and today's episode is about Sablier's Flow, which is a new product they launched very recently. To walk us through it, we have Paul and Shub. Paul, I'm going to hand it to you to, give us an introduction, high level, what is Flow, why we need it, why we should use it.
Hey, Shafu, thank you for having us. So, Sabrier Flow is our new protocol for open-ended payment streaming. So, if the listeners are familiar with Sablier, so far we have shipped Lockup, which is a protocol for closed-ended streaming, which means that like the payments in Lockup had a start time and an end time, and Lockup works great for like fasting and airdrops because you have a predefined period. But with Flow, really what we have achieved is that you can keep the stream open, um, so like open-ended with no end time. It just keeps going. And the trick to make that happen is to enable that. So we track that, and that's how the stream just keeps on going. And then the center can top up whenever they have the funds, whenever they get a reminder from the recipient or whatnot. And yeah, that's it at a very high level. Flow was built with Solidity and Foundry, of course, and we can jump to that during the podcast. But at a high level, Flow is open-ended streaming, and it works great for things like on-chain payroll, subscriptions, any kind of recurring payment that doesn't have like an end time.
Sounds great. So maybe to summarize, maybe lockup is I transfer all my tokens at once and stream that for like 3 months, which works perfectly for airdrops. Flow is I don't know, have like a subscription for Netflix or something that I'm paying on stream, and I have to keep funding that stream in order to keep the subscription.
Exactly correct. So when you don't know when the collaboration between you and the recipient will end, you use Flow. And subscriptions are, like a general example that is easy to understand, but something that is more realistic in Web3 would be things like grants, where just want to pay like a DAO paying like a third party contributor over time, or employees like working Web3 remotely globally that are paid in USDC.
Nice. Oh, interesting. I think, when we entered the space a couple of years ago, we always thought like everything's gonna be on chain, like paying your Netflix subscription on chain. Unfortunately, we're not there yet, right? I don't think anyone really uses streams for that. But yeah, you're right, like DAO stuff, streaming grants. I think that's definitely more realistic. Cool, man. No, really interesting stuff. So Shu, maybe briefly introduce yourself. This is the first time we meet as well. Uh, so yeah, thanks for taking the time as well.
Yeah. So hi everyone, like whoever is watching. My full name is Shubham Yadav, and I joined Sablier last year as a smart contract engineer. Like since then, I worked on like a new version of Lockup, as well as like I worked on Flow from the beginning. So, and it's good to be here.
Very cool. Well, you got a good job at Sablier as smart contract guy. So
Thank you.
so congrats to that. Yeah, for sure.
And if I may interrupt, just like Shub is truly like a 10x developer. I was impressed when I first saw his PRs through our repos even before we hired him. So it is a pleasure working with him, and I'm very glad that he's part of our team.
That's awesome. Maybe let's talk about this for a couple of minutes because I love that. I tweeted this out recently. Like for me, employment is a spectrum. It starts with PRs. And if the PRs are great, maybe it's like a part-time thing, and if it works out, it's like a full-time gig at the end. So really interesting to hear that.
I fully agree with that. So I think if anyone is listening to this and they want to get a job in Web3, the best way is just find an open source repo and look through their issues, and open a PR, and ideally ask few questions, like figure out things on yourself because the team is busy and whatnot. And I mean that's exactly what Shub did. He made great suggestions, and then we met in person and was like a fantastic fit. But yeah, so I think PRs are the way with WEI for for
Like,
yeah.
so I also want to add like one more point. So I wasn't just looking to join a Web3 company. I was actually looking to join Sablier. So like I really wanted to work with these guys, and like I think I really fought for it.
Nice, nice. Well, you chose the right approach. I really love that. PR, at the end, it's the PR, which
Yeah.
really makes a difference. So, no, congrats, man. Okay, maybe we switch to more technical stuff now. Maybe Shub, if you can start sharing your screen and start walking us through the code. I always love looking at Sablier implementations. So this is gonna be interesting for sure. Anything
Yeah, sounds.
interesting about this repo compared to the old one?
Uh, I mean, a lot of things to be honest, because in the old one, like it's so it's just that when you create a stream, you deposit funds upfront, and then and once those funds have been deposited, they start streaming to the recipient. So over a period of time, when the user withdraws from the stream, it calculates like how much amount has been streamed, and if it's like something that user can withdraw, the withdrawal works. But in case of Flow, because we wanted it to be like a protocol that people can start streaming right away and they can like top up like in future. So at the same time, because like one of the main use case of Flow that we have been interested into was the payrolls, and like payrolls in some countries they can be like as low as $1,000 a month, or maybe less than that, and we wanted
Yeah,
to
Shub.
support like those kind of, yeah.
Shub, I love your browser background, but maybe, maybe,
Sorry.
yeah, yeah.
I didn't know that I started sharing the screen. Sorry
All
about that.
good, all good,
Okay,
man.
Maybe we
great.
can scroll to the features
Yeah,
section. Yeah, here we go. Yeah.
yeah. So basically, the objective was to have as much granularity as possible. Like technically, when you look at a token, it has some decimals. So for example, USDC has like 6 decimals, and the minimum you can receive in 1 second is like 0.000001 USDC. You cannot receive less than that, because that's like the smallest unit that USDC has because of the decimal. For example, there is this EUR, Euro ERC20 token, and it has only 2 decimals. So the minimum you can transfer is like 0.01. So that's we call like one unit of that token. And what we wanted to do is to allow users to stream like one token, not like, so we don't want users to stream like one token every second. We want them to be able to stream like one token in like 10 seconds or maybe like 2 seconds. So this will allow you to stream like as low amounts as possible. For example, you may want to stream like $100 a month. So we wanted to make sure that users are able to do that. While in lockup, because like the majority of the use cases is related to the vesting of like tokens, uh, like there is no way that they want to stream less number of like it like they don't want to stream and lock up like one token over a period of like longer period. So that was like big change from lockup to Flow, and when we started working on it, that was like a bigger problem for us to solve as well. So I'll go like come to that later, but for now, uh, so this is like the repo. If you want to go to the Flow repo, it's like on Sablier Labs Flow, and it has a documentation where you can find like all the features, read about it, and then it also has like installation instructions. So before getting into the code, I wanted to like I would like to discuss some fundamental concepts of Flow that will help us to understand like the part of the code base. So if you go to the documentation, we have an overview section where you can like read all about Flow. So it's a debt tracking protocol, which means that when you create a stream, the fundamental uh, part of the stream is the rate per second. You define rate per second, and based on that value, it starts streaming the tokens. And at any point in time, if you want to calculate like how much amount has been streamed, you just take the rate per second and multiply it with the time elapsed. That's how you get the stream stream number, like stream tokens. So that's what it is. And it has, like as Paul mentioned, you can create the stream, you can deposit later on. If you want, you can also deposit upfront. It has flexible duration, which means that when you start a stream, you don't provide the end time. You just start it, and then whenever you feel like ending it, you can pause it. So we have a pause function for that. At any point in time, senders, they can like refund from the stream. So any amount that has not been streamed can be returned back to the sender. Void is like a special function. So it is inspired from the real world, how the loan system works. So let's say if there comes a point when sender is not able to fulfill his obligations to the recipient, basically he's not able to like pay him anymore, and the stream has accumulated debt over a long period of time. So anybody, like any of the sender or recipient, can call the void and basically just terminate the stream. So when you call the void, it just set out any like pending debt to zero, and then it just you cannot restart it anymore. And then we have like the withdraw function. So like every stream, it has a balance. When user make a deposit into the stream, this balance increases. Then the stream has a debt, which is like the amount of token that's being streaming. So let's say at any point in time, there are like 100 tokens that's been streamed. That's like the debt, and then sender has only deposited like 20 tokens into the stream. So if the recipient wants to withdraw, he can only withdraw like 20 tokens because that's the stream balance. So that 20 token, we call it like covered debt. Basically, it's the part of the total debt that's covered by the stream balance, and then the remaining 80, we call it uncovered debt. So if you like combine all of like both these values, you get the total debt. So these are like more related to the user, and then we have something called a snapshot debt and a snapshot time. They are more related to the contracts architecture. So like when a certain functions are called, we take a snapshot of some values, and then we take a snapshot of debt, and then we take a snapshot of the timestamp when the function is called. The debt is called like the snapshot debt, we call it snapshot debt, and then the time when we take the snapshot, we call it a snapshot time. So if you like, because snapshot debt is basically whatever the debt has been accumulated until that point in time, we just like take the cumulative value and store it on the snapshot debt. So at any point in time, you can also calculate total debt as the sum of snapshot debt and something that we call ongoing debt. So we have the snapshot debt, and then we have a snapshot time. We can just like in the future, we can take the difference, that how much time has been passed since the last snapshot was taken. And if you multiply it with rate per second, you get something we call ongoing debt. So basically the part of the debt that is still ongoing, and the snapshot debt is what the total debt that at the last snapshot. So if you sum these two values, you also get like the total debt. So I explained like what the ongoing debt is, and then a flow, because it's a perpetual stream, you can like do anything. You can pause it, you can start it. Like it's like quite flexible. Like it doesn't have any that there is there is not a fixed sequence of function that you can call on it. You can basically call like any function on it as long as they either to certain restrictions. So feel free to ask like any question if you have in between.
Just wanted to make a
So
comment that
yeah,
debt is just the internal terminology we're using for what the user in the UI sees as streamed amounts. Debt is just the ERC20 balance. It's like ERC20 balance is amounts. Is just how we refer to the internal variables that track how much was streamed and how much is covered. We use the term debt because that is what the protocol does. But I just wanted to clarify that debt equals streamed amount.
yes, that's right. So let me take you through the code, and then because now we know what these debt terminologies are, we can now look at the code and have a look at it. So like we have the same structure lockup. Like we have a source file which has all the source contracts, and then there is tests. So let me so in source we have two files. One is NFT descriptor. So unlike lockup, in which it's a dynamic so in lockup we have this dynamic SVG, which
Yeah, Shub,
changes. Yeah,
could you zoom in a little bit more?
sorry. Oh,
Could you
okay.
zoom in a little bit more?
Is it good?
One more time.
Better now?
Perfect.
Okay, great. Thank you. So in lockup, the NFT metadata, it's like it changes with over time based on how much has been streamed and whether the sender has canceled it or not. In Flow, like right now, what we have done is that we just display the Sablier NFT logo, and in the future we will also try to come up with a dynamic implementation of NFC descriptor. Another file is Sablier Flow, which is like contain all the functions that users will interact with, starting from create to refund. Like everything is in this file. This file, it doesn't have storage, so for that we use a base contract. So base contract has all the storage variables. You can find like aggregate balance, stream ID, descriptor, fee, everything. And then it has some modifiers. And then it also has like all the getters that you can use to read the value from the storage. So all the getters that you'll find there, they basically just read value from the storage, with the exception of like admin functions. So it also has like uh, collect protocol revenue, recover. So these are admin functions that only admin can call. Uh, collect protocol revenue, it collects revenue from the protocol if there is any. So recover, we have seen in the past that like sometimes a user can accidentally transfer ERC20 token directly into the contract, which is like bad, because there is no way we can recover it from the contract until there is like admin function. So to solve that, we decided to include a recover function in Flow. It just tracks the combined user balance and like the total balance of the contract, and the surplus amount can be recovered by the admin.
I have a
So, and
question here.
yeah,
Because so I personally have the philosophy, I don't check for user errors in smart contracts, so it'd be interesting to, because it just increases the scope, audibility and stuff. Are there other places where you check for user errors as well?
Good question. And actually, this is not just for user errors. It has happened in the past that we were eligible for like airdrops or rewards because we had like TVL as a smart contract. For example, Aave, we still have something like 150K in a previous deployment that we cannot claim, and that's good money. So it's not just user errors; it's also like just claiming airdrops when they occur, and those airdrops which are allocated towards our smart contract. But on the user error side, Savior being like a payment protocol, there is like a frequent feature request we have received is to stream Aave tokens like AUSDC, which are rebasing, so they change the balance over time. And those tokens, unfortunately, cannot be used with many protocols, including with Sablier. So when they are deposited, whatever interest is earned by the user is just lost forever. I mean, in previous deployments was lost effectively forever. So with this, we can at least rescue some of those, at least for the big users, right? But it's a combination of multiple factors. It's not just user errors. Although I sympathize with your approach, if you are launching a protocol and it's like your V1, don't never mind this user error issue.
Okay, interesting. Yeah, the airdrop one I didn't think about. Yeah, but yeah, it makes sense. You could lose a lot of money. It's true.
yeah, and
Cool.
also the rebasing one.
Yeah.
Yeah, like nothing can stop users from using rebasing tokens to stream, so that's helpful as well. Yeah. So before like diving into the Sablier flow, I just want to dive into the interface. So in the interface we have all the interface like specific, like it basically the contract specifications, and then so for example in Flow we have like all the events
Sorry,
that.
Shub, Before we go, maybe we should explain briefly the folder hierarchy. Like, what we have the abstracts, we have the interfaces. So while we only have two contracts, it's the NFT descriptor and the flow monolith. We have quite a few separate components, and they are in, the abstracts, the interfaces, libraries, and types. And maybe you can explain, why we did this and, how they play together.
Yeah, okay. I intentionally skipped that because that's already covered in the lockup, so like the previous
Well,
podcast. But I'll go through it again. Yeah. Uh, yeah, all good. So like these two contracts are directly in the source, and then in abstract we have like the contracts that are not like part of the flow protocol. Like basically they are not like, they don't have the core functions of the flow protocol, but like functions that are important for us. So for example, the adminable, it contains admin, uh, like the functions that dictate the transfer of the admin, and it also has like only admin. So it's like the fundamental like admin related variables, and these are like standalone contracts, so you can also reuse it in other protocols. So all these files here, except the Sablier flow base, they are like reusable. So the objective is to like keep them separate so that we can reuse them across other repo as well. So adminable has admin, and then we also use batch. So in flow, because like a combination of functions are possible. So maybe users, they may want to like restart a stream, and at the same time they also want to deposit funds into the stream. So like a large number of combinations are possible, and because we cannot implement all of those inside the contract because we have like this limit on the contract size, we decided to implement a batch function. So what it does is that you can pass an array of like call data to it, and then it will make a delegate call to itself. So the flow will inherit, like flow inherits from batch, and when it makes, after it makes a delegate call, it returns values, and we check whether the call was successful or not. If the call was not successful, it reverts, and if the call was successful, then like the state changes. So this is what we implemented in like Flow 1.0, and recently Paul tweeted about it, and because he has large number of followers, people saw it, and then uh, they also like come up with new ideas how we can extend it to, to like how can we make it more efficient. So some of the changes that we are going to do like very soon is like, because right now when it revert, we just like take the byte data and revert in the batch error. So you cannot identify what error exactly it reverted without going to the tenderly and like doing the debugging. So we can like bubble up the actual revert reason and like revert it in such a way that user can actually see it on either scan, like which error like it threw. And at the same time, there are like certain functions that return values, and over here we are not returning anything. So this batch doesn't return anything. So if we have an external integrator who has integrated batch into the contract, they will not be able to check the return value. So we will also decide to return the results from the delegate calls. So that's batch. We also have a no delegate call. So we don't, the purpose of the no delegate call is to prevent any delegation from like outside contract. So we don't want that anybody deploys a contract and use delegate call to make calls to flow. And then, as I explained, Sablier flow base. So the reason we have this
Question.
kind of, yeah.
Why the no delegate restriction? You don't want others to basically wrap the
I mean,
Savior functionalities?
so the protocol, it has a business license, and delegate, if someone like deploys, so what business license does is that it prevents other from deploying the contract. So but people can still deploy a contract which has like delegate call to Sablier flow. So without deploying Sablier flow, they can uh, they can provide all the functions through delegate call. So it also prevents that. Maybe Paul can add to it.
That's pretty much it, right? So
Yeah.
let me clarify that only the core contracts are business licensed, and even so, they can be integrated. So the business license is only to prevent to prevent forks, just people copying and pasting the flow code and deploying it without our approval. But it can be 100% integrated. It can be used. It's public good, right? It's verified on Etherscan. Um, and yes, this modifier simply um, provides a protection against the situation whereby somebody wants to create a clone of Sablier, and do, they don't want to violate the business license. So what they can do is just deploy like a proxy and say, I will delegate a call to the flow contract and just piggyback off our logic. And yeah, we have this protection for that.
Yeah. But like at the same time, batch also makes a delegate call, so it doesn't prevent that uh, because batch is not an external contract. It's inherited by the Sablier flow, so it's a self delegation, and no delegate call prevents delegation from external address, as you can see here. So like all the abstract contracts, they can be found in abstract folder, and then if you are just interested into reading about the functions, they're like net specs, comments, what it does, the requirements, you can find it in interface. And then we have a library which has helper functions and the errors. So error contains all the errors that are used throughout the contract, and helper has some pure functions like which like does some calculations and then returns. So, and then we have types, which contains data types. So let me take you through all the functions that we have in Flow. So like we have these constant functions. So covered that, as I explained earlier, it's a part of the DAT that's covered by the stream balance. Depletion time of, so take an example, if a stream has like 100 tokens and it streams like 1 token a day. So after 100 days, the stream will run out of funds. We call it like depletion. And so depletion time of returns the time when the stream runs out of funds. So in this case, it's going to be like 100 days, but we have a small catch here. So the exact definition of depletion time is timestamp when the stream has actually run out of funds. So for example, if at t equals to, let's say, 100 seconds, if it's going to run out of funds, then the depletion time will return 101. So it's basically an extra second from the timestamp when it runs out of funds. Like this could be useful for the UIs. They can show it in the UI when the user can expect for the stream to run out of money, and then they can like put it in their to-do list that, okay, on this day we have to fund the stream, so that people can withdraw. Ongoing debt, as I explained earlier, it's the part of the debt since the last snapshot. So in this, so because every token, they have their own decimal system, and we wanted to have like more granularity on how much you can stream in 1 second, we decided to have internal variables to always operate at 18 decimals format. So for example, when you deposit like USDC, which has 6 decimals, we don't store it as like the USDC in 6 decimal format. We scale it by multiplying it with 10 raised to the power 12. So it represents 18 decimal tokens, and then that's how we store. So to have a clear distinction between like between the values within the contract, because now we are dealing with 2 decimal system. One is token decimal, another is 18 decimal. We like suffix some of the variables and function with scaled keyword. So it basically means every time you read something that has scaled, it means the returned value has been scaled to 18 decimal format, and if it doesn't have a scale, then we are using token decimal format. So you will see it in a couple of places. So it returns a scaled value of ongoing debt. Similarly, refundable amount returns the amount of tokens that sender can refund. Status of it, so it's like quite useful. So if you want to get the status of a stream, whether it's solvent, whether it's insolvent or paused or like streaming, this is the function. And then we have like all these debts. So total debt, uncovered debt, and the withdrawal amount is how much a user can withdraw. And then we have these non-constant functions. So you can see like at the top, we have all the events, and then we have constant functions, and then we have non-constant functions that changes the state. So it's like really nice way of categorizing things inside a contract. Like I have seen some contract where like people have used, like they don't have an order, and it really makes it difficult to read the contract. So in our case, you will see like all the functions that they are like alphabetically ordered, and then they're like categories, and then within categories they have an order. So you can find like which function like is placed at which location. So adjust rate per second, if you want to adjust rate per second, there are like some requirements, and then it has some notes that it updates snapshot date and time. And then in the dev, we like put everything that we think is would be helpful for the developer, and this is like Solidity net spec. Similarly, we have like create, so it takes sender, recipient, rate per second, token, and whether the recipient can transfer the NFT or not. So when a stream is created, similar to lockup, it means an NFT and transfers it to the recipient, and then that NFT is basically what gives you the authority to, like, NFT is what makes you the true recipient of the stream. So if the NFT changes hands from one user to another, the ownership also changes. So yeah, like you can notice that in create we have a sender, so we don't use message.sender as the sender. Anybody can create a stream between like two parties. Sender doesn't need to be the message.sender. We also have a create and deposit. So although you can use batch to like batch multiple functions, for some functions we decided to we decided to implement functions within the contract. One small difference using batch and create and deposit is that the batch, because it just makes call to like public functions, it will be slightly more gas expensive compared to the functions that we have in the contract. So based on the idea that maybe create and deposit might be more popular function, we decided to implement it within the contract instead of not having it in the contract. So it creates the stream, and at the same time, it deposits into the stream. Then we have deposit. Then we have deposit and pause. You can deposit this into the stream and then pause it. Then we have deposit by broker. So broker is like, broker, like for people who want to build their own UI, or maybe they want to build their own contract to integrate into Flow, and because they are offering like a user experience to their users to deposit into the Flow, they can use this function to take some fee out of the deposit. So basically, the broker, if they want to have a fee charged on their service, they can use this function, and the fee percentage is specified in the broker. It will be transferred to the broker address. Then we have pause, refund and pause. If you want to like refund from the stream and pause it, refund max. So in all the refund functions, user can specify the amount, but in refund max, you will refund, like you can get whatever the maximum amount you can get refund from the stream. Then we have restart. So when you pause a stream, essentially what you are doing is like setting rate per second to 0. That's like pausing the stream. And when you restart a stream, you have to set a new rate per second. So you can pass it through restart. You can notice that some values, such as rate per second, we use a fixed point number because as I said earlier, that like there are like some values which are like denoted in 18 decimal format. So and they have like scale keyword at the end, but because the rate per second, it doesn't have a descaled version. So the opposite of scale is like descaled. So all those values like ongoing debt, withdrawable amount, they can have a scaled or descaled version. But the rate per second, it's like the contract always use the scaled version for it. So we decided to omit like scaled keyword from it and like just call it rate per second, and to signal that it has an 18 decimal, it's an 18 decimal fixed point number. We use this UD21X18 from PRB math. And also the reason that all those variables they are like internal variables of the contract, so user don't have to care about like scaling or descaling. But the rate per second is a user provided variable. It's a user provided input, and we want user to pass an 18 decimal fixed point number for rate per second. So for example, if you want to stream, let's say again 0.00001 USDC per second, you have to multiply it with 10 raised to the power 12, and that's the value that you will pass in rate per second. So it's always scaled version. And then we have restart and deposit. We have void, as I explained, like any party can void the stream if
So
they
sorry to
don't.
interrupt. Just a comment on the UD21X18 type. So the goal there is to prevent bugs where there have been quite a few in DeFi where the input was expected to have 18 decimals, but the developer passed some 6 decimal value, like like an USDC amount, when in fact it should have been an 18 decimal, or vice versa. So you have an error by a fact, like by a margin of 10 to power 12. So with UD2 to 1, we make it explicit to whoever is reading the code that, hey, this is not a normal UI int. Like, do something about it, inform yourself, read what this type is, and we hope that this will prevent bugs. I mean, of course, in our own UI, we know how this works, but for integrators who just look at the Solidity function and they're not familiar with the Sabre as a whole, this should prevent errors, hopefully.
Yeah. And then we have withdraw that user can use to withdraw funds, and then we have the withdraw max, which withdraws the maximum withdrawable amount. So and then we have like Sablier flow base. So this max fee is basically the maximum fee the broker can charge. So we don't want user to put in a situation where the broker is charging like 100% of the fee. Yeah. Okay. Yeah, I completely agree. So so like at the top, all we have like the way we write code is we implement a public function which makes a call to an internal function. So all of these except like depletion time of all of them, they just like make calls to an internal function with the same name. So and this is the status of so let's go down to, and same goes with the like public state changing function. Also, like one benefit is that we specify all the modifiers in the public function. So all the rules that it should have, all the restrictions that we want it to have, they are like part of the like this piece of code. And then the actual logic it's in the internal function, and then that's how it works. So yeah. No, like sometimes they are used in multiple as well. Yes. It's so when you're looking at the code, I know like, okay, this adjusts the rate per second, and all the checks they are like in the public functions. And then if you go to like the actual function, it has the actual implementation. So like I think it improves the readability of the code. Like for some people, they may not be interested into reading the actual logic, like the internal logic. They just want to like skim through the function superficially. So that's my rationale.
Also, in some cases, I think we had the infamous stack too deep issue, and we had to split a function, so it just became a habit.
Yeah. And like also like stack too deep error. So if some function it has like high number of variables, by splitting it into like public and making a call to internal, it avoids that. So that's like another benefit. But here, like as I said, like we have some composite functions. So for example, restart and deposit, it makes call to restart and then deposit. And that's what make it like more gas efficient compared to calling the same using batch. So let's go to like cover that. So in the implementation, like as I said, it's part of the DAT that's covered by the stream balance. So we try to return as soon as possible if like some values are zero. So for example, even though in the end it will return zero if the stream doesn't have a balance, to save on gas, it's better to return it as soon as possible. So if the stream doesn't have a balance, it returns zero. And then if the stream has a balance, then we see what's the total debt of the stream. If the total debt is more than the stream, then the covered debt is basically just the balance, because that's how much a user can withdraw. And if it's the total debt is less than the stream balance, then the actual covered debt is like the entire total debt that user can withdraw. So covered debt essentially is also same as the amount that user can withdraw. It's just a terminology, uh, like because it like for consistency, because we call uncovered debt and then the covered debt. So as you can see here, we fetch the total debt, and then we check whether the balance is less than total debt or not. If it is, return balance, and if not, we return total debt. We also return values as U in 256. The benefit is that, like first of all, we like in the real world, we don't expect the amount, like the actual token amounts to exceed, even though they have like they can have U into 56 as the maximum supply, but we haven't seen any token to have a supply as huge as that. And the actual like realistic supply of the tokens, they are always within U in 128 limit. But the benefit that it offers is that, so for example, you want to add like two numbers, and if they are both like U into 56, they can overflow, and or they will revert. So you have to like add some checks on that. But if you use U into 128 as the data type for values, you can like mindlessly add them, because like the combination, like sum of these two numbers, it cannot exceed U into 56. So it will always fit within like U into 56. So that's like another advantage that it offers. So that's the cover debt. In ongoing debt, so as I said, like ongoing debt is basically the debt accumulated since the last snapshot. And at the last snapshot, because we took the snapshot of time. So the way it works is that it takes the difference between the current timestamp and the snapshot time. That's like the elapsed time, and then we multiply it with rate per second. So because the multiplication, it requires two values to have the same data type, and the rate per second, it like fixed, like 60x18, like a fixed point number, and the time is like U into 56, so we cannot multiply that. So we first unwrap rate per second into U into 56, and then we check if the rate per second is zero, then like there is no point into doing the calculation, because the ongoing debt is going to be zero. And if the snapshot time, if it's same as block.timestamp, that means no time has passed since the last snapshot, so return zero. We have this additional check that the snapshot time. So just in case there is like a bug in the code and somehow the snapshot time is like it's set in the future, which should not be possible, the ongoing debt will return zero. So it's like a safety mechanism for us. And then we just multiply these two values and then return. So do you have a question? Yeah. Yeah. So we have a deterministic script that we use to deploy on chains, and the salt we generate. So we have a way to generate salt. I'll just show you.
Before
So
going to the code, just wanted to explain our approach for deployment. So it's a great question. While we have the deterministic scripts, we actually don't have the same addresses across chains. In fact, we have completely different addresses. And the rationale is
hmm.
that the create two factory that is used by Foundry is not available on all chains. So if you try, I've seen many protocols try to have the same address and then say, okay, it works on Ethereum, it works on Arbitrum, it works on Optimism, but then you deploy to some other chain, and suddenly you can't use that query to factory because it's not available because of some like the way the gas opcodes work or whatever reason they can't deploy it. So um, it gets really massive to have. So imagine you have half of your deployments have the same address, and then the other half have different addresses. So we said rather than have these like incomplete same address like system, we just have complete differentiation. So ironically, we're using deterministic address deployment scripts for that. So we are using Create2, but we are using Create2 to create maximum differentiation. um, so our contracts have all like completely different addresses on all chains. We don't have any two addresses, sorry, any two contracts which have the same address on any chain. And we achieve that by what Shub is going to show now with the salt. So we pass the contract name and the version of that contract when we deploy it, and that ensures differentiation.
Yeah. So we use like FFI cheat code of Foundry, and in the package JSON we have this version. So we read it using FFI, and then the way we create the salt is that we take the chain ID of the chain that we are deploying on, and then we use the version and just like create the string. So that's basically our salt. So on every chain, it's like it's dictated by the chain ID, which is like different for every chain. And for the chain ID, we have an automated way as well. So it should be. It's not in this. So in lockup we have a way, like we have a map of chain IDs in the basic script as well, and that's what it uses. No, actually the chain ID comes from the RPC. So we fetch the chain ID and then we use FFI to read the version. Yeah. Yeah. So let me just like, because we are running out of time, I'll just take 2 minutes to quickly go through this file. So I've like explained main functions. So like one main and the most important function is the withdraw. So in withdraw, like because when a user withdraw, he's withdrawing a descaled version of the amount, and in the contract we are using the scaled version. So there can always be like some residual that's left in the contract because of scaling and descaling. So we wanted to like make sure that there is like minimum loss of tokens to the users, and this approach of like scaling like internal storage to 18 decimal format, it actually it doesn't leave any residual in the contract, because anything that user cannot withdraw because of the precision, it gets stored in the form of like snapshot dat, which is like the scale. So because we are storing everything in the scaled format, it also helps us to provide like the maximum precision to the users when he is withdrawing from the contract. One thing that I want to mention is that, so like we used to have this approach called CEI, which is like check effect interaction. In this, we decided to like add something which is called like protocol invariant version. It's FreiPy. So it's inspired from an article by the Nascent, and I think DYDX also did something like this. So the TLDR is that you have your like check effect interaction, and then you also have something called protocol invariant, which is supposed to be same, like the protocol invariant must hold true at the end of every execution. So like for the beginning, we just added it at the end of the withdraw function. So no matter what happens, the difference in the total debt should always match with the difference in the stream balance, because that's the amount that the user is withdrawing. So this is protocol invariant that we added at the end of the function. In the future, like our objective is to have the same protocol invariant in all the functions. So if like something goes wrong with the contract, like the function will start reverting. Like people won't be like, it will help us like it help us save from the hack. So dydx has this thing where at the end of like every execution, they have a protocol invariant which checks that the user balance are inconsistent with each other, like what they expect. The same idea we are going to implement in this. So, but in this, we just implemented it in Flow. So like you can see that it always makes sure that this check pass.
It's basically having a test in production.
Yeah, like people like we have invariants, but it's like an invariant in production. Yeah, I mean safety of funds, I guess, is much more important. Yeah. So like the tests, it follow the same structure as the lockup. So everything explained in the like previous podcast that applies here as well. But we have come a bit far from there. So I remember Paul mentioning about BTT, where we write trees, and then like we have this tree structure, and then we generate like test file based on that tree structure. Great. Yeah. But in that podcast, do they use any tool to generate the test automatically? Great. Okay. Alex.
That is Alex Cartel. Yeah, we should give a shout
Yeah.
out to
Yeah.
Bullock.
Yeah.
Bullock is an
Yeah.
amazing CLI tool.
Yeah. Yeah. And but we did like one thing that we made Bullock a part of the CI as well. So every time a commit is pushed, it also checks run the CI that Bullock like is being passed. So we have this that the test comply with the BTT in the CI as well. So this is like something new. Yeah. So it's like on the GitHub marketplace. If anybody is interested, they can just use it in the CI. Uh, okay, great.
For
Yeah,
sure.
thank you so much for
Thank you
having
for
me.
having us. Yeah.
Bye.